Okay, I'm going to get started. And the name of my talk is Mortal Kombat and Injustice Story Mode. I'm Adisak Pochanayon. I'm a principal software engineer at NetherRealm Studios, where we make Mortal Kombat. So what is this talk going to cover? What is story mode? There's a full-length feature film rendered in our game with seamless transitions in and out of gameplay. The last two Mortal Kombat titles, as well as our highly anticipated upcoming title, Injustice: God Among Us, have seamless pre-rendered cinematics that transition in and out of gameplay. And this isn't as easy as slapping a movie player over your loading screen. I'm going to talk about some of the technical challenges we had from a post-mortem perspective for the seamless transitions, custom file I/O, minimization of resource contention with simultaneous movie playback and level data loading, pre-caching, offline metadata extraction for hitch-free playback, jitter window detection, and why to multi-thread your movie decoding pipeline. So basically, I'm going to cover all the technology that we used to deliver this seamless gameplay stuff. And there's a lot of stuff to cover in 25 minutes, so I might be talking a little fast. So, well, if a picture is worth 1,000 words, a video's worth more. And I'm going to show you a video from Injustice. It's a new video that we've never shown before. That's going to show seamless movie playback to gameplay, to an in-game cinematic, back to gameplay, and then back to seamless movie playback.
You're all alone, Luther.
Geniuses often are.
Psychopaths like you.
You hero types are all alike, even less imposing close up.
You're testing my patience.
And here the movie's gone to
Resigned to throwing toys.
Damn you!
In-game cinematic.
Time to teach you humility. Quiet, kid.
Making me angry.
Do it again.
Another flexible success.
Don't get it.
And then we go back to movie mode.
Try this on, genius. Superman, report.
It's done. The others are mopping up. I'm taking Doomsday into deep space.
Make sure it's very deep space.
What's that?
It's the none of your damn business alarm.
Radiological. Metropolis.
I can see the headlines. Justice League fails. Cloud kills millions.
You gave him a nuke?
Most of the League dies, and Superman's beloved city is vaporized. I console the masses by offering to rebuild it in my own image of... He was done.
So that's our example of movie mode, or a story mode with seamless playback. And So what you saw was basically the seamless transition from movie and gameplay. In order to be consistent, we render using a game engine machinima style, and we use matching characters, backgrounds, and camera angles to make them as seamless as possible. For the actual render, we use an in-game, in-house PC version of the game. The scenes are actually much bigger than would fit in our 32-bit build, so we allow artists to break them up, render them on a render farm, and do some merging and compositing. There's some issues with this. For example, if they're using chroma key with a green background, we can't use anti-aliasing, or they get green halos around the characters. For our device playback formats, we try to use industry standard formats, WMV, DivX, MP4. We target whatever the hardware can natively accelerate, so for best performance. We mix the audio for all the languages into the single movie file, so we have one file, basically, that contains the movie. And we support surround sound wherever we can. This allows us to actually use standard tools like VLC to view our movies. The one thing I would say if you're going to attempt to do movies during playback and loading is to test off of disk early and often. So the first time we did story mode was MK versus GC. They didn't actually test this until basically 2 months prior to submission, and all of a sudden, when they ran it off disk, it didn't work, because the shortest movie they picked was about 11 seconds long, and we had to load 200 megabytes of data while playing an 11-second movie. So anyway, a lot of our data is compressed for faster loading. We automatically cache stuff to HD to reduce stress. And that 11-second movie came in later, so assets were cached. But that's still a very short time. In the worst case, when the movie doesn't cover the load time, we have an emergency load screen pop up. So we try to shoot for movies to be at least 15 or 20 seconds long. And the situation of not testing off of disk basically meant that we had to completely crunch to get a lot of this technology done. And our PS3 final movie code for MK versus DC was finished less than 24 hours before our submission. So that's a little fun story. We use custom file I/O in our movie playback. So we have a movie file system that has fully asynchronous server thread, runs I/O in the background. There's virtual interfaces, so we can actually change what type of file access we use. We can use in-memory, we can use direct reads off disk, we can use pre-cached movies, read-ahead movies, but the underlying movie player code doesn't know what type of file it's reading. On the Xbox and Vita, the movie player libraries actually allow you to plug in file systems, but on Wii U and PS3, we had to write a custom demuxer front end to the playback. And read-ahead caching is our main optimization, but naive read-ahead caching isn't enough. For example, when you saw that video, at the end of the fight, the next movie played instantly. There wasn't a delay, and even if you have read-ahead caching, when you open a file to play back a movie, there'd be several seconds of delay. So we also allow pre-caching. We know what movie is going to play next, so we can say, preload this movie, and then when we want to play it, it plays instantly without a delay. We had to tune the read-ahead size of the cache, and there's a number of reasons for that, which I'll get into. And also, it's very important to do large reads. You don't want to do small reads. And I'll also cover why we did that. Our cache size varies per platform, just because different movie playback formats need different caching. But why large reads? OK, if you have a disk that has maybe 8 megabyte per second read speed and maybe an eighth of a second seek time, that's actually fairly standard for slower disks out there in the real world. Well, 64K reads have horrible throughput. If you have seeks between every read, you get 0.5 megabytes per second throughput. Just going to 1 megabyte reads, you get 8 times more throughput. And 2 megabyte reads, you'll get 5.3 megabytes per second. It's not as dramatic of an increase, but it's really important to have larger reads than 64K. What else is important with I/O? Well, we actually gathered some data. And I'm going to show you what that was. But again, eliminate seeks, reduce your number of reads, do larger reads, disallow OS read slicing. This is very important on Xbox. If you issue 2 reads at the same time, let's say 2 different threads or 2 different processes issue 1 megabyte reads, it will slice them into 64K chunks, and you'll get the worst case performance. And you also want to examine your data for unusual patterns. So here's one pattern that we see on Xbox. The read pointer for video and audio diverge. They're not quite the same, and those two lines are the read pointers, and the bottom line is how much they diverge by. We call this jitter, and in this file we get about 5 megabytes of jitter, but the worst is normally 8 megabytes. However, when you're using unconstrained VBR, you can get large spikes in jitter. Here's a case where we had 13 megabytes of jitter, and that blew out our read-ahead cache. The worst we've ever seen with unconstrained VBR, though, was 27 megabytes. So don't use unconstrained VBR. Constrain your bit rate, and you won't get that problem. Now, also with unconstrained VBR here on the PS3, you can see a large spike in data rate. Unconstrained means that the rate could vary depending on the needs of the scene. And in this case, the artists were doing a lot of cutscenes, and each cutscene required basically a keyframe. There were 9 full camera cuts in 10 seconds and 4 cuts in a 2-second period, which required 40 megabytes of data to be read in a 5-second window. And that was actually pushing the physical capacities of the drive. So that's also bad. But typically on PS3, we don't get problems like that, but we do have a problem where you can have an uncached read at the beginning of the file, that big spike that you see there. And what is that? That is metadata. Basically, when you open a file on PS3 for DivX, it reads all the way through the file to the end of the movie to find some data about the movie. And that didn't work. That wouldn't work for us. So we wrote a PC tool to locate this metadata, separate it out so we could pre-cache it when we pre-cache the movie. But similar problems can happen on MP4 and other file formats. You just have to tell it, like in MP4 box or FFmpeg or whatever you're using to compress, to relocate your move atom and your metadata to the front of the file. So that's some of the file issues we had. We also had issues with CPU bog. So we're loading the game assets and decoding and doing things like garbage collection while the movie is playing back. Now, garbage collection can take several frames all by itself. So one of the things we had to do was be able to detach the movie player so it could run asynchronously. And what we did was we had it run in the render thread, and the render thread would detach while loading was happening. We still render the movie as a texture, so Scaleform can display it, and we can display stuff on top of it, but we did everything in the rendering thread. And this way, if the main thread stalls, we don't have spikes. Another thing we do is we use push and not pull for movie data throughout the data path. Now, what is pushing data? Pushing data basically is when you have independent asynchronous threads that work on data and push it to the next stage. The difference is this is like thread-based versus a pulling data approach, where you pull, like once a tick, you'll call do work or something like that, and you'll ask for data from the previous thread. If you had a movie decoding pipeline, like the one here, these little brown boxes would each be like a do work function, and the bottom box is all the audio do work functions. Well, if you're ticking those just to pull, if you don't tick them often enough, audio will stutter. We actually helped Batman Arkham City with some problems in their movie playback. One of the things was they were using tick functions like this, and they were asking for 1/30th of a second audio for each tick. In their PAL 25 build, they only did it 25 times a second, so they got stuttering. Our simple hack was to turn off frame locking for PAL 25, because not that many people use PAL 25, but it's important to consider. Our pipeline, these yellow boxes, are places where we replace this polling mechanism and pull data with push data and asynchronous threads. And you also see that I added a thread there for the async file caching because the file server runs in a separate thread. So we actually have this many threads on our Wii U decoder. On some of the other decoders, like the PS3, the video read and audio read are combined into one thread. Now, when we did the detached rendering that I was talking about, the render thread runs separately. So basically, it's a 100% asynchronous pipeline that is just pushing data throughout the entire movie player, so there can be no stalls. Another thing we had to worry about is memory savings, because we're doing our movie playback during the time that we use the most memory, which is loading and instancing data. We use custom heaps for the movie player to avoid fragmentation. And when we're not playing back movies, we actually allow this heap to be used for other systems. We try to minimize the number of read-ahead buffers, and there's less work required with the read-ahead caching. We also work in native YUV format. So why YUV format? Well, if you have RGB buffers, when you do YUV, there's 2 channels that are 1/4 the size each. And so it uses half as much memory. And basically what we do is we get a picture that looks like that instead of RGB. And you can see that 2 of the channels are much smaller, and we just recombine them into an image. So I have 2. We do the YUV conversion in a shader. I'm just going to show you 2 formulas here, but you can find these in any SDK documentation. This is NV21, and this is NV12. But another thing we do is gamma correction, and we also could do that in the shader, because some platforms like Vita supported the YUV conversion, but they didn't do gamma correction. So basically, we just add a line like that to our shader at the bottom, and that did the gamma correction for us. The next thing I'm going to talk about is GPU fencing. So we have these textures that we're using for output buffering, but at first we double buffered them, but that would cause tearing. And it's important to know why this can happen. First of all, like Xbox doesn't support D3D lock discard on a PC. That'll get rid of tearing. But we use multi-threaded renderer. We have a game thread and a rendering thread. So let's say our game thread updates the movie texture on frame A or N, and then passes it off to the rendering thread on the next frame, and then updates texture B. The rendering thread creates a drawing list for the GPU, and the GPU is going to draw frame A at the same time that our game thread comes around to updating it again. So that causes a conflict. Double buffering isn't good enough there. And as you can see, the conflict just continues. Now, triple buffering might work for you, but the way to be safest is just to actually use GPU fencing. You can basically use N buffering or whatever, and you might actually need more buffers if you're doing H.264 decoding anyway, because there's reordering of frames and stuff like that. So I want to recap some system limitations that we ran into, that you might run into. If you're doing stuff on Xbox 360, the file I.O. can only be overridden on an XMV movie player, XMV2. It'll try time slicing large reads, so you have to only do 1 large read at a time. This is an interesting one. We were issuing commands from 1 thread and using overlapped I.O., and then we were doing a teardown because basically it happened during our load and garbage collect. Overlapped I.O. on the Xbox 360 will fail if the issuing thread that started that I.O. was killed. Another interesting thing is you don't get pause on your movies if you don't have an audio track. So if you have a movie without audio, just put a silent audio track in, and that's the only way you can pause it on 360. On the Vita, we just used standard H.264, but we could only use 3 reference frames and no B frames. And there were some spurious file reads, but we just cached the very beginning of the movie and always left it cached, and that got rid of that. The PS3, one of the things we actually had to do was we had to do a custom demuxer based on their sample code. Sample code is very rarely production ready, so we had to do a lot of massaging of that code, basically. And the Wii U, we had to write the decoding pipeline from scratch. So one of the things was like their demuxer only supported 1 language, but we have 5 audio languages, so we needed to write our own front end to handle that. We had to handle crazy things like resource swapping, core affinity. You can actually swap the entire main process out of memory, so there's like this foreground, background swapping. There were the out-of-order frame decode issues because we were supporting B frames. And we also ran into some hardware bugs. So we ran into a bug with the H.264 decoder. It couldn't run when the GPU and DMA were running. Those are being fixed in an upcoming SDK, but they weren't fixed soon enough for us, so we had to go around them. And we also had some issues with Fmod and AX for audio. So I know that was a lot of stuff. I spoke fast, and hopefully we're done at the end of the day. But if you have any questions, I encourage you to ask me or give me a card and ask me later. That's it. Any questions? Hopefully that wasn't too fast for you. I tried to get it done in 25 minutes. Okay, I think we're done. Thank you, everyone.